Let's talk about the concentration of hydrogen and hydroxide in pure water. By the way, this symbol, the brackets, represents concentration in chemistry. So that means the concentration of hydrogen ions. This means the concentration of hydroxide ions. Now, I told you that if you had a sample of pure water, that the dissociation of those molecules occurs very rarely. So if we were to measure the concentration of the hydrogen ions and the concentration of the hydroxide ions in a sample of pure water, we'd find about this many grams per liter, which is the same as saying molarity. Now that number is difficult to understand, so we put it in scientific notation and we get 10 to the negative 14 molar. In other words, how much hydrogen and hydroxide can we find in a typical sample of pure water? 10 to the negative 14 molar. Now this 14 is important. Because of this number, our pH scale, which we use to measure acids and bases, is only going to go up to 14. 14 is the upper limit for this. 14 is going to be your magic number for this section. Another thing that's important to understand is that the concentrations of hydrogen and hydroxide in any solution are indirectly related. So that means that as the concentration of hydrogen goes up, the concentration of hydroxide tends to go down, and vice versa. We can use this to help us determine the concentrations of hydrogen and hydroxide in a solution. For instance, if we have a solution and we've measured that the hydrogen concentration is 10 to the negative 5th molar, then that means that the hydroxide concentration is going to be 10 to the negative 9 molar. Now, how did I know that? Well, 5 plus 9 equals 14, and 14 is our magic number. Next, let's talk about the pH scale. The pH scale is sort of a simplified way of describing how much acid or how much base is present in a solution. Now we've got two chemicals we could measure, right? We've got hydrogen and we've got hydroxide. So which one does the pH scale use to measure this? Oh, that's terrible. Well, it uses hydrogen ions. This is all based around the presence of hydrogen. Now here's the formula for the pH scale. pH is equal to the negative log base 10 of the hydrogen concentration. So what does that mean, and why do they use this crazy system? Well, consider this. If we had a solution and we knew that its concentration of hydrogen was 0.001 molar, that's a little bit difficult to understand. Now, we could simplify that and say that it's 10 to the negative 3 molar. That's a little easier to understand, but still kind of hard to wrap your head around. If you take that number and you put it into this formula, it's going to tell you that the pH is equal to 3. 3 is a number that's easy to understand. So that's the reason that they use this complicated formula, is because it takes these big crazy numbers and it turns them into numbers that are easy to understand. When you are given the hydrogen concentration, I want you to remember that the pH is going to be the same as the exponent. So if you're told that the hydrogen concentration is 10 to the negative 3, remember that the pH is going to be 3. pH is recorded in positive numbers only, so if there's a negative on that exponent, you just ditch it. And the scale goes from 0 to 14. How do we read the pH scale? Well, let's start right here in the middle. Chemicals that are neutral have a pH of 7, and water is a great example of that. Now remember that water has an equal concentration of hydrogen and hydroxide ions. That's what makes it neutral. Acids are chemicals that have a pH of less than 7, so 7 all the way down towards 0. And acids are going to have more hydrogen than hydroxide. They have more hydrogen than hydroxide. If we add hydrogen to a solution, it becomes more and more acidic, and its pH is going to get closer to 0. So closer to 0 means more acidic. Now on the opposite end of the scale, we have bases. Bases span from 7 up to 14. Bases are going to have more hydroxide than hydrogen. If we either removed hydrogen from solution or we added more hydroxide, which does the same thing, the pH is going to get higher. So less hydrogen means a higher pH number. More hydroxide also means a higher pH number on the scale. Incidentally, living things tend to have pHs of between 6 and 8, depending on the type of cell you're talking about. There are exceptions to this. Of course, the inside of the stomach is somewhere between 0 and 2, and that's just normal for the stomach. Because the pH scale is logarithmic, it's a base 10 system. That means that if I move from one number to another on the pH scale, I'm changing by a factor of 10. So let's consider these examples. Let's consider a solution with pH of 6 versus a solution with pH of 7. The solution with the pH of 6 is going to have 10 times more hydrogen in that solution than the pH of 7. If I go from 7 down to 5, well, it's going to have 10 100 times more hydrogen in it than a solution with pH of 7. So it changes by a factor of 10. I'd like to have you practice with this a little bit more before you move on. So see if you can use that pH scale, that base 10 system, and answer these questions. The last thing we need to consider in this chapter are these things that we call buffers. Buffers are chemicals found in natural systems. We also use them in the lab. And what they do is stabilize pH. They minimize changes in hydrogen and hydroxide concentration in a solution. Now, buffers consist of both an acidic component and a basic component, and they kind of work together to keep the pH at a certain range. The basic component will accept hydrogen ions when they are in excess. So if the pH of a solution starts to go down because there's more hydrogen all of a sudden, these chemicals will absorb that hydrogen and raise the pH back up, so it's about at the same level. The acidic component of a base, or a buffer rather, will actually release hydrogen ions when they are depleted. So if the pH starts to go up in a solution, meaning that the hydrogen ions are all being taken up, the acidic component can release hydrogen and make that pH go back down. So it's at about the same level. The most common buffering system found in your body is called the bicarbonate buffering system, sometimes called the carbonic acid buffering system. Where does it come from? Well, you have water in your blood. You're made of about 70% water. And your tissues are constantly producing CO2. CO2 is a waste product. When water and CO2 combine, they make this chemical called carbonic acid. Now, carbonic acid can be useful as a buffer in the body because what it can do is it can break down into an acid component and a basic component known as bicarbonate. Now, why is that useful? Well, let's say that the pH of your blood starts to go down. You start to build up a little too much hydrogen. The bicarbonate portion of this system will take up that hydrogen and bring the pH back up. Let's say that the opposite is happening. You've got a little too much hydroxide building up in the system, or your hydrogen's disappearing. The acidic component of this system will begin to release hydrogen, and that will help bring the pH back down, so it stays at about the same level. Now, ideally, you want your blood chemistry to stay at about 7.4, and that's what this system does. There's this pseudoscience-y idea floating around on the internet known as the alkaline diet. The alkaline diet claims that your body has a particular pH and that it's healthful to maintain this pH by eating foods that are also at that pH. Now, there's several things wrong with this. Your body doesn't have one pH. Different organs have different pHs depending on what their job is. For instance, the stomach is very, very acidic, but the small intestines tend to be pretty basic because they have different jobs. Also, your body has these different buffering systems in place to maintain the pH of different organs. So no matter what you eat, your body has ways of dealing with the acidity and alkalinity of these chemicals. Now, it's not to say that eating really acidic food all the time is good for you. You know, things that are high in acids can increase tooth decay, and they can cause heartburn if you have problems with that. But in general, no matter what food you eat, your blood pH is going to stay at 7.4 because that's what your body does. As long as your kidneys and your lungs are functioning well, your blood pH is going to be just fine. Now, I am not a doctor, so if you have concerns about your diet, if you have concerns about your body, go and ask an actual doctor. But in general, it's fine to not buy products that use this pseudoscience-y idea. Things like alkaline water that are supposed to be healthier. People buy pH strips and they carefully test the pH of all their foods. That's pseudoscience as well. You don't have to do this to remain healthy. But again, if you have concerns, go see an actual medical doctor. In this Your Turn, I would like you to return to that Acids, Bases, and Buffers learning module and work your way through the buffers section. This can get a little complicated, so take your time with it and answer the questions that are in your guided notes, and we'll work with it more once we get into the class. This is the end of this chapter, so once you've completed this, you are ready to come to class and do the work. We'll see you then.